Hello, welcome back to today's discussion on cytochrome P450. In the last class we were discussing this very important metalloenzyme known as cytochrome P450. We have seen a nice and crystal clear structure of cytochrome P450 with the camphor as the substrate. As you have seen, here is the porphyrin ring, iron center is at the middle and there is a proximal site. At the proximal site this cysteine is attached. As you have seen in case of hemoglobin and myoglobin, exactly similar porphyrin ring is there, but over here you will have histidine as a side chain. In this case this cysteine side chain makes it really interesting for its chemistry. As you have seen, when histidine is there in case of hemoglobin and myoglobin, this iron center with histidine is capable of reversibly binding oxygen and deliver that oxygen towards the center where it is necessary. In this case histidine is replaced by this cysteine and we will see that upon oxygen binding at this distal site. So, again this is the proximal site, this is the distal site. So, at this distal site upon oxygen binding, this oxygen will get reduced by this iron center and subsequently it will try to react with the organic substrate. Now, the orientation of this organic substrate in front of the active site will dictate which CH bond to be hydroxylated or to get functionalized. So, in that particular case, in these cases or any enzyme, these side pocket which are not really directly part of the main active site plays crucial role in dictating the reactivity pattern on this substrate. As you will see, for a radical type of mechanism, a tertiary CH is more preferred over secondary and secondary is more preferred over primary. But all of these cases in case of the substrate binding pocket, substrate orientation with respect to the enzyme active site and perfect positioning of these two component, that is means the reactive component as well as the reactant, that is substrate, is quite important. As you have seen, cytochrome P450 type of enzyme not only capable of hydroxylating a particular organic substrate, it can also promote a series of related events. Number of reaction or type of reaction that cytochrome P450 can carry out is almost countless. We will see a list of reaction today where cytochrome P450 can play a role and a crucial role. I hope you got that this is a porphyrin center and iron in the middle. So, heme iron center with the cysteine binding, thiolato binding, this is the site which is responsible for the chemistry. We did not show here any oxygen species yet because this is the crystal structure that obtained. Obtaining crystal structure with an oxygen binding is always very difficult because those are very reactive intermediate and the binding may not be too strong, and therefore getting a crystal structure is next to impossible. Although many attempts have been made to get these crystal structure. Usually to get these unstable crystal structure, one needs to cool down the reaction solution so that the desired other reaction can be slowed down significantly. In addition, since these are reactive intermediate that is going to be generated from reaction of iron and oxygen, eliminating the substrate or replacing the substrate with some another organic substrate which can inhibit the desired reaction, desired let us say in this case hydroxylation reaction, that would be quite useful, because in presence of the inhibitor maybe the desired reaction can be prevented partially or completely. In particular for cytochrome P450 cases, these are very reactive intermediate that forms at the iron center, therefore preventing a desired reaction is always extremely challenging. Let us look at what we have discussed in the last class. Of course, we have discussed about the oxygen molecular orbital, and these lone pair or unpaired electron are responsible for the triplet ground state of oxygen, and once these oxygens are getting reduced by one electron, that electron will be coming in one of these two orbitals, right. These are degenerate orbitals. If it is doubly reduced, that means a peroxo species is formed. So, the mono electron or one electron reduced species is called superoxo, 2 electron reduced species is called peroxo. Once it is reduced by 2 electrons, then 1 electron will come over there, another electron will come over here. So, overall that would be the molecular orbital diagram of oxygen 2 minus, that is the peroxo. If it is 1 electron reduced, that would be the superoxo or superoxide species. In the whole process, in converting oxygen into some useful compound such as aliphatic substrate can be converted to hydroxylated product, you still need to have a second oxygen atom reduced subsequently to form the water. So, these 2 electron that is required to reduce this terminal or the second oxygen atom to water molecule, that is taken care by this relay of electron that happens towards the active site, as we have discussed in the last class. So, the electron hopping or transfer throughout the chain and up to the iron sulfur protein happens, and from there on it provides the electron whenever required for the oxygen reduction process at the heme iron center with cysteine bound center in the cytochrome P450. Let us look at some different type of reaction that we have discussed in the last class. So, if you are taking an organic substrate such as aliphatic substrate, it can be reduced. So, this is from a review article. Okay, we have the review article, yeah, I think one of these review article, yeah, okay, that is mentioned over there, Chem Review 1996, that is the article. Let us go back. Okay. So, Chem Review, this is from Chem Review 1996, where hydrocarbon hydroxylation can be occurred. So, this is a summary of the cytochrome P450 reaction. Here you see that a CH bond can be reacted to give the COH, aliphatic substrate hydroxylation chemistry. This is one of the easy to understand reaction. So, where a hydrogen atom abstraction at this center will occur, and the OH iron 4 hydroxo that gets generated over there undergo rebound to give the C hydroxylation reaction. One can think of taking an olefin as a organic substrate as opposed to this aliphatic sp3ch bond. These iron oxo species that you have seen getting generated in the last class, that iron oxo species, these are high valent iron oxo species, iron 5 oxo, you cannot talk it as a iron 5 oxo, it should be a iron 4 oxo with porphyrin radical cation being there, can transfer the oxygen atom to give you the epoxide species. If you are taking a terminal alkyne, let us say phenyl acetylene or alkyl acetylene moiety, it can be subsequently transformed to the corresponding terminal carboxylic acid. That is quite phenomenal reaction, I will say, and you see this is and quite interesting kethyl intermediate that is proceeding for the reaction. So, abstraction of the CH bond from this and the rebound of the hydroxo and then subsequent rearrangement will give rise to the C double bond O intermediate. So, let me draw that reaction just quickly. So, if we are trying to draw this reaction, it would be, so C triple bond CH we have, and then R we do have, and let us say this iron oxo intermediate is there. This should be iron 4 oxo with a radical cation which is essentially iron 5 oxo. So, this will gives rise to the abstraction of this species, and we will have Rc radical plus this species will be giving rise to iron hydroxo. This is going to be an iron 4 hydroxo. This radical and this hydroxo then combine. So, iron 3 hydroxo getting generated, iron 3 hydroxo is getting generated, and this C radical and this hydroxy radical will form a bond together. So, overall it will be iron COH. So, this is the oxygen that is coming from there. So, this is the oxygen coming from there, and then deprotonation would lead to the intermediate where you will see RH double bond C double bond O is forming, right. So, this is a quite simple and effective reaction and then upon hydrolysis at this center one can think of reacting it with of course this will go and that will come back. Overall this is going to give you the terminal acid moiety along with this CH2OR moiety, right. So, what we have seen right now over here is the formation of such terminal oxide species, and that gets generated from this species, right. So, what you have seen, this intermediate is reacting to give you RCH2 CO2H, terminal carboxylic acid is getting generated from this reaction. If there is an arene ring, so arene epoxidation or aromatic ring hydroxylation and along with NiH shift it will happen. So, what happens over here is the oxo species that is over there. So, it can undergo electrophilic aromatic substitution reaction at this olefin center to give the epoxide moiety, which can then undergo either NiH shift or the overall phenol formation upon subsequent rearrangement and removal of HX, right. If you are taking N-methyl or N-alkyl amine, it could be a secondary amine as is here, or it could be a tertiary amine. This amine can have reaction with the iron 5 oxo or iron 4 oxo radical cation intermediate, where this is the aliphatic sp3 center. This can react and the hydroxy moiety can rebound with it or bind with it. This hydroxo then can undergo further reaction to give you the formaldehyde. This CH2OH unit gets to the formaldehyde, and the ND alkylation occurs in the whole process to give you the aliphatic amine or primary amine. Primary amine, it could be aliphatic and aromatic depending on the R. So, N-dealkylation chemistry can also happen. Another very interesting reaction which we may have seen in different contexts is that the S-dealkylation chemistry can also happen. As you can see over here, this thioether RSMe can be also reactive towards this high valent iron oxo species to give you RsCH2OH moiety. Now, this RsCH2OH moiety can then further undergo a cleavage of this C alkyl bond upon further rearrangement formed from this unit and so this NDS dealkylation can also be possible, right. So, overall RSH is getting generated and formaldehyde is coming out from the reaction. Similar to S dealkylation and N dealkylation reaction, one can think of doing O dealkylation reaction. For example, if you have anisole, you can get phenol. If you have thioanisole, you can get thiophenol and formaldehyde. If you have anisole, then this methyl unit, once again similar to the S dealkylation chemistry, it can undergo the sp3CH hydroxylation chemistry upon CH activation or CH abstraction. In this case it is a radical mechanism which can give rise to the COH to OH and ROH, overall HCHOH generated. So, we have discussed briefly in the last class. Let me discuss one more time here in brief that is. So, if you have this high valent iron oxo intermediate, it could be iron 4 oxo and then radical cation, whatever way you are ready to write, radical cation at this center and in the porphyrin unit, right, in the porphyrin unit, and you can take an RH. Okay. Now, this RH can undergo the reaction with it. So, overall let us say, just for clarity, I would write it down as iron 5 oxo and the porphyrin moiety over here. So, it can give rise to the iron 4 hydroxo, right. So, if you are breaking it down, it is going to be iron 4 O dot and this H dot over here picks up to give you that, along with R radical formation. Now, this R radical formation then can undergo. So, this is the species, okay, not that one, you have to draw like that, and then further this homolytic cleavage if you want to draw it. So, this is a iron 3, of course it will not stay as it is, over there it will pick up a water molecule from the media, and then RH R radical and this radical half a bond will give you the ROH formation. If you are doing O18 leveling, in these cases you will end up getting O18 leveling from the oxygen moiety. So, as you have seen, this this iron 5 oxo has come in turn from the iron 3 hydroperoxo species, right, where this was also, let us say, if it is labeled oxygen or O16 or O18 depending on where it is coming, in turn that has taken a proton and an electron and from iron 3 superoxo it is getting generated, right. In the last class we have seen, and that is in turn getting reacted with iron 2 and O2 if it is O18 leveling. If it is O18 leveled O2, then all the way up to the product, this O18 leveling will be getting reflected. So, this iron 2 species, iron 2 porphyrin complex, once it is formed, okay, of course there is always a porphyrin ring. Once this iron 2 porphyrin ring is reacting with the oxygen, then this oxygen will be getting reduced by 1 electron to form iron 3 and the superoxo intermediate. So, this is the superoxo intermediate. This superoxo abstract a hydrogen atom or picks up a proton and electron from the system. Electron is coming from, let us say, this iron sulfur cluster that we were discussing a moment ago, and this electron and proton. So, it forms a first iron 3 peroxo species, then gets protonated to give the iron 3 hydroperoxo intermediate. Now, this iron 3 hydroperoxo intermediate can then further cleave to give the hydroxide and the iron 5 oxo, which is necessarily iron 4 oxo with a radical cation on the porphyrin moiety. So, porphyrin ring has a electron cloud and conjugated electron cloud. That pi electron can be oxidized pretty easily to give the radical cation, as well as the iron 5 gets let us say reduced by that electron to give the iron 4 radical cation oxo intermediate, which is essentially iron 5 oxo. And for the clarity purpose, for our discussion purpose, it can be concluded that, and then the RH which can be over there can react through, which is sitting right over there, can react with iron 5 oxo to give you iron 4 hydroxo and R dot. Over here a water molecule will react with this ROH overall to give you R dot OH or ROH molecule. Okay. So, this is what the mechanism is for the substrate RH to ROH formation. So, as you can see, RH is getting reacted with this high valent iron oxo intermediate to give you the ROH species. Okay. We have seen this similar mechanism previously, just to say that this O18 labeling is also quite interesting. So, similarly this hydroxylation chemistry as you are seeing over here, it can be followed quite easily. It can be followed quite easily, and one can follow up this chemistry either on the alkyl, S alkyl and O alkyl species, or even the N alkyl species. In case of the N hydroxylation chemistry, similar chemistry can happen. Once again, the one of the H over here will be replaced by OH. Over here one of the H is replaced by OH, that is sp3CH. This is sp3CH replaced by OH. Once again this is sp3CH replaced by OH. This is more of a epoxidation type of chemistry, like olefin epoxidation, electrophilic aromatic substitution type of reaction that is happening, epoxide formation and subsequent rearrangement gives that. And in case of the alkyne, once again the CH bond is getting cleaved and getting hydroxylated as we have just discussed, and giving rise to the overall terminal carboxylic acid formation, which are, I believe, quite successful and quite efficient transformation of synthetic arena. Okay. So, we have the N hydroxylation chemistry and the N oxidation chemistry. As you see, if you have an imine or equivalent species, it can form the N oxide. If you have sulfur oxidation, of course sulfur N dealkylation or S dealkylation is possible, dealkylation type of chemistry is possible. In addition, sulfur can be oxidized further to give you the sulfoxidation species. So, all this reactivity essentially trying to tell us is that cytochrome P450 is a very reactive intermediate. For example, this RSMe, if it is reacting with let us say if it is reacting with SMe with iron oxo high valent. So, what can happen that this sulfur, this lone pair electron can just oxidize to give you the sulfoxide Rme and iron 3 species, right. So, if this was iron 4 radical cation where, so iron 5 oxo, then this upon transferring the oxygen it becomes iron 3. So, these are again very fascinating reactions, and it is quite exciting to see that a versatile reaction or a series of great reaction can be performed by cytochrome P450. But remember, the major problem of the cytochrome P450 is really we are having quite a lot of reactivity. As you can see over here, this reactivity is not limited to a particular organic substrate, it almost reacts with every organic substrate. So, that is going to be quite a challenge, and minimizing such reactivity can be extremely difficult. So, if you have aliphatic substrate it reacts, if you have olefin it reacts, if you have alkyne it reacts, if you have aromatic ring it reacts, if you have N alkyl it reacts, S alkyl, O alkyl, primary amine, secondary amine. So, this is primary amine, this is secondary amine. If you have tertiary amine, of course it will react to give the N dealkylation product. If you have an even imine, it can form N oxidation, it can form the S oxidation also to give you the sulfoxidation product, not only S-dealkylation product. So, as you see that even with one substrate different types of reaction it can do. So, it is a very reactive intermediate, and thanks to that iron high valent oxo species. In these cases it is equivalent to iron 5 oxo species, right. So, we will get back to that once again little later, but what is important to understand that the cytochrome P450 in turn has helped us in biosynthesis of many different natural products. For example, if one is looking for biosynthesis of the CO bond just like this, one can perhaps think of having an epoxide formation over there, and then this phenol which was over here then can attack. So, an epoxide over here and the attack can form the CO bond. Similarly, one can think of doing the CO bond formation starting from the phenol, either from this side or from this side. Let us say if it is a diphenol, then the epoxide formation over there and subsequent attack by the phenol can form this bond. Similarly, a carbon-carbon bond can also be formed in this vancomycin by this cytochrome P450. Indeed, 3 units of cytochrome P450 can be active on this vancomycin to gives rise to the reaction product or the final vancomycin synthesis, right. So, in the last class also we have seen how different how different organic substrate that is getting incorporated into our body and then further can be reacted with cytochrome P450. For example, by mistake or by accident, if this benzopyran molecule is getting incorporated in our body, then this highly conjugated and highly of course delocalized pi electron system, which are relatively easy to react with a high valent iron oxo intermediate, it will end up reacting as if like this is an olefin, isolated olefin in a way. So, this olefin can be reacted with the iron 4 oxo, or in this case iron 5 oxo equivalent, to give rise to this epoxide ring, which can then ring open to give the cis hydroxylation intermediate, which again can give rise to this epoxide formation at this side, which is truly isolated olefin double bond, and this epoxide formation and further damage, further ring opening can ensure that such molecule, benzopyran molecule, can interact with the DNA, and during this formation and or via this formation it can react with DNA itself. It may not be reacting with the DNA, but this species particularly is going to be very reactive, or this species derived from this is going to be very reactive and is going to damage or intercalate, interact, bind with DNA, and is going to destroy the DNA significantly. Alright. So far we have seen that these reactions are quite powerful. Just like last reaction, we have seen that in even the camphor type of substrate, which can be crystallographically characterized and can be hydroxylated quite easily by utilizing this enzyme. Alright, we will come back and discuss this reaction, beautiful reaction, slowly with respect to the cytochrome P450 activity. I hope you will keep studying this, and we will start here on the camphor substrate in the next class. Thank you very much.